Hi, everybody. This is Dr. Nigro with the screencast of our notes dealing with the law of conservation of energy as part of our work and energy unit. To this point, we have discussed what energy is. We have talked a little bit about kinetic energy and potential energy. We should understand how to calculate kinetic energy using the formula 1/2 mass times velocity squared. And we have discussed gravitational potential energy, which is the potential energy due to the height of an object above the Earth, which is equal to the mass of that object times the height above the Earth times the gravitational field of that object. And for us, that has been the Earth. We also have discussed the units of energy and how that is equal to a joule. So what we're going to do next is talk about how energy within a system has to be conserved. So let's start with that, the definition of the law of conservation of energy. So that law states that energy cannot be created or destroyed. All right, so similar to what we saw with matter back in chemistry, all the energy that we received as part of the Big Bang is all that we get. We can't make any more, and we can't destroy anything that we have. So it cannot be created or destroyed, but energy can be transformed into a different form of energy. So a great example of this is when you drove to school this morning. When you pressed on the gas pedal in your car, gasoline was injected into your engine where it underwent a combustion reaction. That combustion reaction led to breaking of bonds within the gasoline molecule. And that potential chemical energy was transformed by your engine into a variety of different types of energy. Some of that energy was converted into mechanical energy and it helped spin the rotors and your axles so that your tires will spin. Some of it was converted into electrical energy, which runs your dashboard, your radio. Some of it was converted into heat energy if you had your heater running, and some of it was lost through other forms of energy such as sound or heat. But the key is that all the energy that was present in those gasoline molecules had to be transformed into some other form of energy. We didn't destroy any of that. It went somewhere. All right. So when we think about that idea of transformation, we know then that there must be a total amount of energy within a system. All right. Now, we're not going to get into chemical energy or radiant energy or heat energy too much. We're going to focus on mechanical energy. And when we talk about mechanical energy, that total mechanical energy present tends to be equal to the potential energy of an object plus the kinetic energy of that object. All right. Now, the total energy is constant. All right. Once you determine what that total energy value is, it remains the same throughout the motion of that object. All right. The potential energy and the kinetic energy, however, these two are going to vary. All right. And they do so inversely or indirectly. All right. So in other words, if at any point during the motion the potentially increases, then the kinetic energy must be decreasing. Or if at any point the potential energy decreases, then it's the kinetic energy must be increasing. But in the end, the sum of these two must equal that total energy. All right, so that's a really key concept here. Once you identify the total energy present within a system, it does not change. That number will be used over and over and over. The kinetic energy and potential energy values, however, will be changing. Okay, now the way we're going to look at this idea of conservation of energy is to think about riding a roller coaster. All right, I have videos posted of working through this idea of conservation of energy with a roller coaster. So if you would like to go watch that and then come back to the notes, that's perfectly fine. Go check Google Classroom. If not, let's just do a thought experiment. All right, so let's say we're sitting in the car of a roller coaster and we're going to go up the first hill of that roller coaster, and there's a chain underneath our car that grabs the car and drags us to the top of the hill. So the question is, well, why? Why do we need that chain? What is the chain doing? All right, well, the chain is providing energy needed to move that train to the top of that first hill. All right, now later we're going to talk about that energy specifically is called work. So the chain is doing work, but we'll get to that in a little bit. All right, now as the roller coaster goes up that first hill, it's gaining height. And once it reaches the top of the hill, all that energy that was put in by the chain is now potential energy of the car sitting on top of that hill. It has height, we have mass, we can calculate what that potential energy value is. And it sits there for just a second. And then the train goes over the top of that first hill and heads down that first hill. And as it does that, do you think it's going to speed up or slow down? Right? Well, if we think about riding a roller coaster, it seems pretty obvious that it's going to speed up. And that makes sense because at the top of the hill, you're not moving. And then as you go down the hill, you move. So that means your velocity value must be increasing. All right. So as we go down the hill, we're going to speed up. All right. So as the train goes down the hill, what does that mean in terms of the potential energy? What is it converting into? All right. So our potential energy will be decreasing as we go down the hill because we're losing height, but it can't just be destroyed. It's got to be converting into something else. And in this case, it's converting into kinetic energy. All right. So now we've reached the bottom of the hill. We're going pretty fast and a loop is right in front of us. So we're going to go into the loop, up and over, and then back out of the loop. All right. So as the train goes through the loop, where is the train's velocity the lowest? All right. Well, we're moving pretty fast as we come into the loop, and then we're going to slow down as we go up to the top of the loop, and then we're going to speed back up as we come out of the loop. So the train's velocity should be the lowest at the top of the loop. Basically, wherever we have the most height, that's where the train will be going the slowest. That doesn't mean it's not moving. It just means it will be going the slowest. All right. As the train goes through the loop, where is the train's kinetic energy the highest? All right. Well, there are two spots. When you enter, the loop and when you exit the loop. All right. So in other words, when you're at the lowest position in terms of height, that's where you should be going the fastest. And again, this is that whole idea of potential energy grows and kinetic energy declines, and then potential energy declines and kinetic energy grows. All right. Throughout the ride, what remains constant? Well, that is our total energy. That remains constant throughout, and we represent that with a capital TE. All right. The roller coaster must follow the law of conservation of energy. And this means that throughout the ride, the total energy is equal to the sum of the potential energy and the kinetic energy. So if I can calculate that total energy, then I know one of the two, potential versus kinetic, I can figure out the other. And then from there, I can figure out things like height or velocity. Why do you think that the first hill of a roller coaster is the highest? Why can't a later hill be higher? All right. So if you think about a roller coaster, generally speaking, the first hill, the one the chain drags you up to the top of, is the highest throughout the ride. And the reason is the total energy. That first hill, that potential energy due to gravity, is going to be the greatest at the maximum height. And so if we have a really high hill at the beginning, that sets the amount of total energy that we have throughout the ride. All right. So we need as much total energy as possible. Oops. All right. Remember, height equals an increased potential energy. All right. So the higher the hill, the more total energy we have for the ride. All right, now the second part, why can't a later hill be higher? Well, think about it. If you have a certain amount of energy and then you go down and then you come back up and you try to go higher than you were before, you don't have enough energy. You don't have the amount of energy you need to reach a higher height, if you want to think of it that way. All right, so the car will not have enough energy to go up a higher hill. All right. Now, some of you may say, well, I've actually been on a ride where a later hill is higher. That only happens if there's another chain. If you have a higher hill that you need to go up, or you've lost enough energy through things like friction, then a chain will be in place and it will do some work, provide some energy, and drag your car to the top of that higher hill. But generally speaking, most of these roller coasters work by having a very high hill at the beginning, because that gives you a large amount of total energy to work with as the car moves through the rest of the ride. All right, so now I have a figure of a roller coaster. It's a simple one, which is two hills. All right, and what we're going to do is, using the letters A, B, C, and D, we're going to answer these questions, A through E. All right, so looking at the figure of the roller coaster to the right, answer the following questions. At which point, A, B, C, or D, does the roller coaster have the most potential energy? All right, so we know that potential energy is equal to mass times gravity times height. So if I want a high potential energy, then I need the highest height. So if I look, A is at 45 meters, B is at 22 meters, C is nearly at 0, and D is at 32 meters. So A is going to be the highest. So most potential energy. At which point does the roller coaster have the most kinetic energy? All right, so kinetic energy, if I want a, sorry, a lot of kinetic energy means low potential energy. So I need the lowest value for the height. So if I look, that's going to be C for this particular ride. It's the closest to the ground, so it should be moving the fastest at that point, because the potential energy will be the lowest, which means the kinetic energy will be the highest. At which point is the roller coaster's velocity increasing? All right, so definitely not A, because it's not moving yet. But as it comes down the hill, for B, it's going to be losing potential energy and gaining kinetic energy. So we'll see an increase in the velocity. At point C, it's starting to go back up the hill, which means it's going to be gaining potential energy, which means it should be slowing down. And D, it's continuing to move up. So again, it will be gaining potential and losing kinetic. At which point does the roller coaster have equal? Now, this is a good question. Equal. All right, now it's not perfect here, but what we need is a point where the height is basically half of its maximum height, because at that point, the potential energy and the kinetic energy should be equal to each other. All right, our maximum height is 45 meters, so I would say that point B is going to be the closest. All right, that's just under half of the maximum height. All right, so we'll say half of max height. All right, at which point A, B, C, or D does the roller coaster have the most total energy? Now, this is a trick question. All right, we know that the total energy is constant throughout the ride, so it should be the same at all of these positions. All right, remember, constant. All right, so that's just a thought process of working our way through a ride. Now what we're going to do is some math. We're going to use the information in the figure again, but this time we're actually going to do some calculations. All right, so as a reminder, potential energy is mass times gravity times height, and we're going to use 10 meters per second squared for our gravity value. All right, our kinetic energy formula is 1/2 mass times velocity squared. So if we're solving for velocity, that's going to be equal to well, I should say velocity squared, is going to be equal to 2 times the kinetic energy divided by the mass, and then we'll have to take the square root. And then in the total energy is going to be equal to the sum of the potential energy plus the kinetic energy at any one point throughout the ride. All right, so we've been given the height values for these different points. We know that the mass of the car is 1,000 kilograms. All right, so I'm going to use that height and my formula for potential energy to calculate what the potential energy is for the car at position A. All right, so 1,000 times 45 times 10 gives me 450,000 joules worth of energy. All right, now this is maximum height and the car is not moving, so it has no kinetic energy. And the total energy is the sum of potential plus kinetic. All right, so this and this added together tell me that the total energy for the ride is 450,000 joules. All right, now I know that total energy is constant throughout the ride, so that means that it is the same for all of the positions. So that 450,000 is good for each one of those positions. All right, now for velocity, if I have no kinetic energy, then I have no velocity. Okay? All right, now we're going to look at position B. So we've come down the track some. All right, we're moving, so we're going to have kinetic energy this time. But we're going to start by calculating again the potential energy using that height, the mass, and then gravity. So 10 times 1,000 times 22 means I have 220,000 joules of potential energy. All right. But I know that my total energy is 450,000. So the kinetic must be the difference between those two numbers, which is 230,000 joules. All right. Now to find the velocity, this one's a little trickier. I'm actually going to go down here and do it. You can ignore the work part. We'll work on those notes later. All right, the kinetic energy is going to be equal to 1/2 the mass times the velocity squared. So I can use this formula to solve for that velocity. I start by plugging in the 230,000 joules for the kinetic energy, and that's equal to 1/2 times 1,000 kilograms, times the velocity value squared. All right, so I'm going to take that 230,000, I'm going to divide it by 1/2, and then I'm going to divide it by 1,000, and I get 460, and that's going to be equal to v squared. But I need to take the square root of that number, and I find that the velocity of the car at position B is around 21.4 meters per second. All right, so now I'm going to look at position C. We just designated C as 0 meters. It's a little more than that, but just for our purposes, all right? If we have 0 meters of height, then we have 0 potential energy. We are on the ground, all right, which means all of that total energy, that 450,000 joules, must be kinetic energy. So I have 450,000 joules of kinetic energy. All right, I'm going to repeat the calculation I just did, except this time I'm going to have 450,000 joules. So I'm going to take 450,000, I'm going to divide it by 0.5. All right, and then I'm going to divide that by 1,000. So I have 900, and I take the square root of 900, and I see that my velocity is now 30 meters per second, which makes sense because I am lower, I'm closer, I'm actually on the ground, so I should be going faster than I was at position B, and I am. All right, for my last one, position D, I'm at 32 meters above the ground. I calculate the potential energy by mass times gravity times height, and I find that I have 320,000 joules of potential energy, right? But I have 450,000 total, so the difference between those two is the kinetic, which is 130,000 joules of kinetic energy. And again, I use my formula for kinetic energy to find that velocity. So 130,000 divided by 1/2. Then I divide that by the mass of 1,000. I have 260. I'm going to take the square root of that value, and I find that the train is moving at 16.1 meters per second. And I asked myself if that's reasonable, all right, compared to B and C. So at position D, I'm higher off the ground than I am at B or C. So I should have more potential energy than kinetic, which means I should be moving slower than I am at either of those two positions. And if I compare, that is the case. Okay. So when we're dealing with the mathematics of a system, you have to keep in mind the formulas for potential energy and kinetic energy. And you need to remember that the total energy of the system is constant. So once you calculate that value, once you know what that total energy is, it's the same value throughout the ride, throughout the motion of that object. It does not change, right? It is the biggest place where people mess up. They try to change that kinetic energy. The total energy. And if you do that, then you're going to miss the problems. Okay. All right. So that is it for our notes on conservation of energy. There'll be some worksheets to work on in class, and we're going to do a couple labs to help support this. But if you have any questions, please don't hesitate to reach out and ask.